Hello guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easier to understand. Today we're going to see an introductory problem on the continuity equation. The idea is quite simple. We have a turbine, represented by this guy here, and we have steam coming in, and we have steam coming out from two different outputs. And the idea is to apply the continuity equation to find what are the outputs in terms of mass flow rate and volume flow rate. Now, the continuity equation tells us the following. If we have a steady state, okay, so that is, we have a state in which we have a constant flux of mass coming in and out of our control volume, which is our case here, okay, if you take this as being our control volume, then that means that all the mass that's coming into this guy eventually leaves this guy, right, from one of the exits that's possible. In other words, we won't have water accumulating inside this control volume, inside the turbine over time, and we won't have the amount of water that's inside. We're always going to have that constant mass, so we're not going to have the amount of mass increasing in the control volume over time or decreasing, that is, more mass leaving in respect to what's going inside. Okay, that's the idea behind the steady state, and that's when the continuity equation can be applied. So let's read the problem statement. A steam turbine receives 5 meters cubed per second of water vapor at 3 megapascals, 600 Celsius. The turbine has an intermediate phase where steam is extracted. The temperature and pressure of the steam in the extraction pipe are equal to 200 Celsius and 600 kilopascals. The pressure and the quality in the main discharge pipe of the turbine are equal to 20 kilopascals and 90% respectively. Knowing that the mass flow in the extraction pipe is equal to 15% that of the incoming vapor, and that the speed in the main discharge pipe is 20 meters per second, we are to determine the volumetric flow rate in the extraction pipe and the diameter of the main turbine discharge. So it wants the volumetric flow rate, let me highlight this, on the extraction pipe and the diameter on the main discharge. So write this down quickly. So volume flow rate, I'll define like so. Okay, volume with the dot to indicate it's a rate instead of V, because we also have velocity in this case, so not to be confused, right? So I'm going to use vol for volume and V for velocity, and the diameter of one of the states. So note that we have water coming in, okay, vapor coming in, steam coming in here, and then we have two like different places in which the steam is coming out, right? We have a discharge pipe there, we have the main discharge. So this is the one they call extraction pipe, and this is the main discharge. All right, so I've named them state 1, 2, and 3. And I want you guys to notice that we have these states completely defined on every single instance, okay? 3 megapascals and 400 Celsius, so we have two thermodynamic properties, independent ones, 200 Celsius and 600 kilopascals, completely defined, and we have 20 kilopascals and quality of 90%, okay? So we can grab all the properties we wish for these guys here. That's 100% okay. Now, the other thing is that because of the continuity equation, because the mass is not staying inside that turbine, well, we can say that the mass flow rate, one, that is the amount of water coming in, has to be equal to the sum of the other two discharges coming out. Another way to think of this is like so. Let's draw quickly my turbine. Just draw a little box for the turbine. What's coming in? Well, we have state 1 coming in, and what's leaving in terms of mass, not in terms of energy, just in terms of mass. In terms of mass, we have the extraction pipe here, which we call M2. So mass flow rate M2 for the extraction pipe, and a mass flow rate M3 for the main discharge. And incoming, we have mass flow rate 1. So all the continuity equation is telling us is that the delta M has to be 0 as well. So in other words, what's going in, M1 minus what's going out, M2 minus M3, has to be equal to 0. Okay, so in other words, the mass that coming in M1 has to be equal to the mass that's leaving from M2 plus M3. Okay, what else do we know? We have an extra bit of information, which is that it's 15%, right? What is there? Why is it saying that? Right here. Okay, so we know that the mass flow rate in the extraction pipe is 15% of the incoming vapor. So this guy here in the extraction pipe is 15% of this guy here. So we can write that as well. Let's write that as a second bit of information. So we know that the mass flow rate 2 equals 15% that of mass flow rate 1. Brilliant. So what we can do now is we can relate these volumes and these masses and find everything we're looking for. We don't need to do any energy balance in this case. Volumetric flow rate for the extraction 1, that is volumetric flow 2, so this is what we're after, and also the diameter on the main discharge pipe, that's diameter on 3. Okay, let's start with the volumetric flow rate. I'm going to note that because of, I can find the mass flow rate 1, because I know the volumetric flow rate of 1, and I can easily find the specific volume for 1, okay? You don't need to memorize this, just look at the units, right? The volumetric flow rate, that's meters cubed per second, and the specific volume is meters cubed per kilogram. So you note that the meters cubed go away and we're left with kilograms per second, right? And that's exactly the mass unit for the mass flow rate. So that means that if we take the 5 that we already have and we divide by the specific volume, we can find the mass flow rate. And let's just make sure we know what these guys are. As I said, they're completely defined, and they are. but let's just make sure we know what are the states, whether it's saturated, compressed, or superheated. State number 1, 3 megapascals and 400. So I have the table down here. We're going to look for the 3 megapascals, that's a 30 bar, right? And you'll see that, this is a superheated table, sorry, let's go to the saturated one. Sorry, there you go, 30, right here. And you know that the saturated temperature is 233. Our temperature is 400, right? So our temperature is 400. That's greater than 233. So we know that state 1 is, so state 1, super heated. Cool. Next state, state 2, 600 kilopascals. So let's go to 6 right here. And the saturated temperature is 158. Our temperature is 200. So again, same thing, right? 200 greater than this. Therefore, state 2, super heated. Okay, so those two are superheated. And state 3, the main discharge, that's 20 kilopascals and quality of 90. So we know that it's not superheated, right? Because it has a quality, we know by definition that's going to be a mixture. This is the pressure here, 0.2 bar, same thing as 20 kilopascals. And then we know that our specific volume for that guy there is going to be 90% of this, and then 10% of the liquid that we can grab later. Okay, so state 1 and 2 are superheated, so I need to go to the superheated table. That's why the superheated table is here. For state 1, so that is state 1 here, which is a 30 bar or 3 megapascals, our temperature is 400, so I'll be looking here at 400, and these are the properties that I can get for state 1. I'm interested in the specific volume, which is 0.093. Is that 300? Oh, it's 600. My apologies. Not sure what I had. 400 there, 600. Okay, so going back, not this column here, but this column here, 600. Okay, and our specific volume is 0.1324. Great, so that's the one we're looking for. Remember, this is specific volume 1. So if I divide 5 by 0.1324, I can get the mass flow rate 1. And I got this to be 37.76. And that is, like we checked, kilograms per second. But now know that we have only 2 equations and 2 unknowns, right? Because we know this information here, we can find M2 with that, and then we can use this one to find M3. So as easy as that, let's do M2. That might be too thick. There you go. M2 is 15% of 37.76. So M2 has to be 5.66 approximately. That's also kilograms per second. And if I apply the continuity idea, then M2 is whatever is coming in. Sorry, M3 is whatever is coming in minus whatever is leaving on the extraction pipe. And that difference is 32.1 kilograms per second. Amazing. So we have all the mass flow rates. Now, our unknowns, remember, trying to find volume flow rate on the extraction pipe, so volume flow rate 2. What do I need to that? Well, we can use exactly the same idea as this guy here, right? This guy here, because I know the mass flow rate, and I can find specific volume. If I do that, then I can find the volume flow rate. Volumetric flow rate, so let's try it the same way, right? The mass flow rate on 2 is the volumetric flow rate 2 divided by the specific volume on 2. So therefore, the volumetric flow rate on 2 will be equal to specific volume 2 times the mass flow rate 2. We know this guy, just need to grab this guy and be on our way. So state 2, that's superheated as well. We know that's 600 kilopascals and 200 Celsius. So that's why I have this 6 bar here. So this is the same thing as 600 kilopascals. We're looking for the 200 Celsius. So this column here is the one we're interested in. And within this column, we're interested in the specific volume. So this value here, 0.3522 meters cubed per kilogram. Okay, so the volumetric flow rate will be the mass flow rate, 5.66 times the 0.3522, which gives me 1.9934, and it goes on. 34 and goes on. We can approximate that. So the volumetric flow rate 2 is approximately 2, right? 1.993, so that's good enough to go to 2. So 2 meters cubed per second, right? Checking units, always do that. So this guy is kilograms per second, and multiplying that by the meters cubed per kilogram of the specific volume. So meters cubed per second. So this is one of the answers we're looking for. Next part, we're looking for the diameter on the main discharge pipe. Remember that if we have, think of it looking down the pipe, right? So this is the cross-sectional area here. So if we have a certain velocity going through this pipe, so going on the direction through the screen here, and then multiply that by the area, what we're going to be finding is actually a volumetric flow rate, right? So the volumetric flow rate can also be understood as an area, the cross-sectional area, multiplied by the velocity, right? Transverse velocity in respect to that area. So we have the velocity on 3. And we also know that this, from what we just did, right, is equal to the mass flow rate times the specific volume. So if we're thinking for 2, these are all going to be for 2, obviously. We can think of it as the cross-sectional area on 2 times the velocity on 2 will be equal to the mass flow rate of 2 times specific volume on 2. Excuse me, 3, right? This the main one, not the extraction one. On 3. All right. Now we can convert the area because we know that an area is just pi r squared or pi diameter squared over 4, right? Over 4. This is diameter for 3, and that's what we're looking for. So in other words, we can rewrite this and solve this for the diameter, and it's going to look like so. The diameter of 3 squared will be equal to the mass flow rate for 3 times the specific volume for 3 divided by the velocity for 3 times 4 and divided by pi. Okay, so we have all this information. The only one we're missing at the moment is the specific volume for 3, which we can grab. Okay, so let's grab that, and then we can finish off this problem. Specific volume for 3, we know that 3 is a mixture, so we can do VF plus X in the difference for G minus VF, or we can do the old-fashioned way, which is just, it will be whatever is steam times the specific volume of steam plus whatever is not steam, 1 minus X, times the specific volume for the liquid. And they're the same thing. So let's grab these two fellows that we need, this guy and this guy, because we know that X is 90%, 0.9. So for the steam one, we can go where we were before. We're looking at 20 kilopascals right here, and this is the one we're looking for. 7. So we're going to take this guy and multiply by 0.9, right? So we have 90% of steam. And then the 0.1 is liquid, and that's going to be a small influence. So I have the table down here for the properties for water. We're looking at 0.2. So we don't have 0.2, but we have 0.199. And remember this always, times 10 minus 2. And this is the specific volume for the fluid, or the liquid. Okay, so 0.001017. And you know that this is going to be such a small one. This is 10% of this guy, right? So it's 10 times divided by 10, the 0.001017. That's a very, very, very small contribution. So it doesn't really matter whether we do the interpolation here or not. You can do it. You can find an even more precise value, but you'll see the end specific volume is not going to change because our specific volume for 3 will be 0.9 that multiplies the 7.648, and that's the one for the steam, plus the 0.1, 10% remaining, that will multiply 0.001017, was it? Yeah, 1017. Okay, so note that this is going to be just very small compared to this. And indeed, I got the specific volume 3 to be 6.88 per kilogram, and that's what we're going to plug in over there, 6.88. So let's do this. Diameter will be equal to the mass flow rate, that's 32.1 that we found before. Specific volume that we just found, 6.88. 4 is a constant. No unit there. Velocity was given in the statement as 20, and then pi is a constant as well. Unit-wise, what do we have unit-wise here? We have the mass flow rate, that's kilograms per second. The velocity, meters per second. And the specific volume, meters cubed per kilogram. Seconds with seconds, kilograms, meters with meters cubed. We're going to be left with meters squared. And that makes sense, right? Because we're squaring the diameter still. So whatever we get out of this is the square of the diameter. So it's meters squared, makes sense. And what did I get out of here? 14.8059 keeps going. And we're going to take the square of that. And we take the square of that. This is meters squared, right? So the diameter 3 will be the square of that guy there, the 14.0. And this gives me 3.7496. Let's go ahead and round it up to 3.75. Okay, there you go. So now we know the diameter on the main discharge pipe. That's 3.75, and we also know the volumetric flow rate on the extraction pipe. Hope this was useful. If it was, make sure you're subscribing to the channel and sending through questions so that I can help you out.